In this episode, we are going to look at some important concepts in matrices. So what are these concepts? First, if we have our matrix given as A, say matrix A 4 2 1, say 0 1 2 and 5 3 4. There are some terms and concepts we should understand before we can do something huge about matrices. So our first thing we are going to consider is what we call the principal diagonal. The principal diagonal. So we know that a diagonal line or a diagonal divides the shape into two. Are we okay? So we are going to find a line which is going to divide the matrix into two. So how do we identify where this line will pass in terms of matrix? So first, let's look at such a matrix. So assuming we have a matrix A in the form, say A11, A12, we have some matrices around, and we have a matrix still A1n. This represents we have a number of what? Columns. Remember, the n is the column, m by n. Same way, if I have A12, this is going to be A21. A21, the second row, the first column. And I have A22. There are some matrices there, and we have A2n. Second row and a number of what? Column. Let's assume some matrices are also around this place, and we have AM, a number of what? Row M by the first column. And we are also going to have AM2, leaving some matrices around. And the last one is AMN. Are we okay? So in this way, how do we identify the principal diagonal? And the principal diagonal contains the entries element as. So to identify the principal diagonal, you are going to find it with the elements, say A11, A22, A33, A44, and the others. Are we okay? So looking at this A11 is the first point in order to identify the principal diagonal. This A22 is also the second point up to the last point. Are we okay? So looking at this line becomes the diagonal line for the matrix. So this is the principal diagonal. All the elements falling within or on this line are going to be the numbers for any analysis. Are we okay? So now that we know, let's look at a matrix and try to find out its principal diagonal. So say 1, matrix B is giving us 3 5 8, and we have 24 1 0 2 3. In order to identify the principal diagonal, the element A11, we have A22, and the element A33. They are going to be the members on the principal diagonal. First, let's see the order of this matrix. This is a 3-row by a 3-column matrix, 3 by 3 matrix. So let's identify one by one. A11, this is A11. This element A22, the second row, second column, second row, second column. Third row, third column. This is third row, third column. So this is the principal diagonal. Are you okay? All right. So another example say matrix C is giving us 2, 4 and 5, 7. So our principal diagonal is going to be 1, 1, 2, 2. The order of this matrix is 2 rows by 2 columns, 2 by 2. So our A11 is the first one, and our A22 is the second row, second column, and this is going to be our principal diagonal. Are we okay? So all this falls on the principal diagonal line. So this is how we identify our principal diagonal. Are we okay? We can try more examples on this. We are going to use this idea to find the determinant of a matrix. So it is better we know how we can identify the principal diagonal. So let's look at another matrix, say a matrix A, which is equal to, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 0, 0, 1, 2, 4, 5, 6, 7. So this is a matrix, right? Matrix A given this form. First, let's find the order of the matrix. This is how many rows? 1, 2, 3, 4. 4 rows. 1, 2, 3, 4. 4 columns. Are we okay? So this is a 4 row, 4 column matrix. First, we know that our principal diagonal is going to lie on the A11, A22, A33, and A44 up to the number of order. So A11, this is the number. Second row, second column. Second row, second column. This number falls there. Third row, third column. It is this number. Fourth row, fourth column. This is it. Meaning the principal diagonal is lying and all these numbers fall on the principal diagonal. Are we okay? Can we find the principal diagonal for this matrix B? Two, 4. And say a matrix C. First, this matrix C, what is the order of this matrix? This is a 2 row, 1, 2, 3, and the 3 column. So if we are to find the principal diagonal, first, looking at the examples that we've made or we've tackled, we have what we call a square matrix. A square matrix. A matrix which has M equal to N. The number of rows is equal to the number of columns. Are we good? With this type of matrix, we can find the determinant. So this is the row is equal to the number of what? Column. By looking at this example, the number of rows is not equal to the number of what? Column. Therefore, it is very difficult for us to find the principal diagonal. Are we good? All right. So with this, we can find our principal diagonal anytime we have a perfect, say, matrix 2 by 2, 3 by 3, say 4 by 4, and 5 by 5. Are we good? So by in this course, we are going to limit most of our analysis to a 2 by 2 and a 3 by 3 matrix. Let's look at another important aspect. These are just introductions that we are trying to figure out some special concepts. So in case you are to find a principal diagonal or identify a principal diagonal, you'll be able to go through and we can start any process. So let's look at another important parameter. So equality of matrices. Equality of matrices. Let's look at the equality of matrices. When do we say matrices are equal? So two matrices are said to be equal if they have the same order and the corresponding entries are the same. So one, they have the same order, and two, corresponding entries are equal. Such matrices are said to be equal matrices. For example, matrix A having 2, 4, 8, 1. Matrix B having 2, 4, 8, 1. So here we can say matrix A is equal to matrix B. Let's see if they obey the laws. One, they have the same order. This is 2 by 2 matrix, 2 rows, 2 columns. This is also a 2 by 2 matrix, and the corresponding entries are equal. At A11 is equal to B11. This is A11, this is B11, and that is equal to 2. Also, our A22 is equal to B22, and that is, where is the second row, second column? This is 1. Second row for the B, second column, and that is also 1. So the entries are all equal. Are we good? So such matrices are said to be equal matrices because they have the same order. Pay attention to the order, and corresponding entries should be equal. Okay, so can we look at example again of a matrix in the order? We have 10, 8, 5, and 2, 5, 6. We have 6, 2, 23 for say matrix A, and matrix B is also giving us 10, 8, 5. We have 2, 5, 6, 6, 2, 23. So are these matrices the same or equal? Yes. So matrix A is equal to matrix B. Any element you pick at a corresponding entry, they are equal. So say A23 should be equal to B23. What's the order of this matrix? This is a 3 by another 3 matrix. The same way we have 3 by 3 matrix. So second row, third column. This is second row, third column. That is 6. This is second row, third column. That is 6. So that is 6. But bear in mind, you are not going to check for only one of the entries to see if it is equal, then it qualifies to be the matrices are equal. No, you have to check for all the entries or the element to see if they are corresponding to each other, and check for the order too if they are the same. The order can be the same, but the entries may differ. That does not make the matrix equal. For example, if we have a matrix C as 0, 4, 1, and we have matrix D as 4, 0, 1. What is the order for matrix C? This is 1 row, 3 columns. So this is 1 row. So a row matrix. This is also 1 row, 3 columns. So first, the order are the same, it qualifies. But the corresponding entries, are they equal? Looking at A11, it is not equal to, or looking at C11, it is not equal to D11. A or C11 is 0, but here D11 is 4, meaning these two matrices are not equal matrices. They do not obey these parameters, so they are not equal. Very good. So we can try other examples and see if our matrices are equal matrices. Then we can boldly do any analysis. So that's for the equality of matrix. These two conditions must be satisfied. Now let's look at sub-matrices or a sub-matrix. So a sub-matrix. What do we mean by saying a matrix is a sub-matrix? Any matrix obtained by omitting some rows and columns from a given matrix is called a sub-matrix. So one, we omit rows or a row, and we omit some columns or maybe a column. Such a matrix is said to be a sub of a matrix. As the word goes by itself, sub meaning part of a whole. So for example, if we have a matrix A giving us 6, 7, 8, say 1, 2, 3, let's extend this 4, 2, 1 as matrix A. Then our sub matrix B can be obtained as 1, 2, 4, 2. This is a sub matrix of A. So B is a sub matrix of A. How? Looking at A, this part is what we are using it to form matrix B. So this row is omitted and this column is omitted. Therefore, B is a sub matrix. Very good. Example 2, let's say a matrix C is of the form 5, 1, 0, 8, 2, 1, negative 1, 5, 3. Then we have a matrix D as 1, 0, 2, 1. Then D is a sub-matrix of C, because looking at this, this is the portion or the part that is forming matrix D. We are omitting this column and we are omitting the third row. So a matrix which is obtained from one other matrix by omitting some rows or a row and a column or some columns, then that matrix is a sub-matrix. Can we say this matrix is a sub-matrix? Let's look at this. We have a matrix A to be 5, 6, 0, 1, 4, 5, 8, 9, 2. And we have matrix B as 5, 4, and 9, 2. Is matrix B a sub-matrix of A? No. Matrix B is not a sub-matrix of A because looking at this part, this 5 is here. Although 9 and 2 correspond, but 4 and 5 are different entities and different positions. So B is not a sub-matrix of A. Pay attention to the positions when it comes to matrices. The position matters. So B is not a sub-matrix. Are we good?